directly influencing on the accuracy and the build time. Of course, we need to strike the balance between build time and the accuracy while selecting your layer thickness. So it is directly influencing on that. So then the another aspect which we need to consider, and of course, support structure is another aspect here which we need to consider. Say if you vary the part orientation, so then you may have a different quantity of the support material it requires. But again, you may not eliminate the supports, but you could able to minimize the supports maybe by adopting some kind of design rules or some kind of say what you call, so you have some thumb rules to be followed, and again it may vary from one technology to other technology also. Why? Because predominantly it depends on the raw material that you are using it. Some process you may use powder, some process you may use filament, some process you may use a liquid, and then you may use a different physics altogether for one technology to other technologies. And so then we cannot generalize saying that if you're having this geometry, so then it's going to be the best suited design. But you cannot generalize. So why? Because it will vary from technology to technology. So then somehow then we need to understand, this part is going to fabricate on which machine and which model. Also it may vary. Then in that case, like, which we can understand thoroughly about the aspects of this support structure and how it is getting, say, minimized, that can be done. Like then we need to have some kind of experience or some kind of what you call some skill set. Definitely it is needed, maybe by experience or by the user of that machine, that technology. Somehow we need to, why? Because again, you don't have a ASTM or any other standards to be followed. Like, this is the thing, that is another aspect which we need to consider. But anyway, so let us focus on the first parameter, that is the part orientation, then how it is getting influenced on your quality of the 3D printed parts. And of course, so how do you get evaluate, or how do you choose the optimum orientation? You may come out with several situations or the criterions. So like, say, one criteria may be the part height criteria in the build direction. Means, say, if your Z height is minimum, say, of course, it will reduce the number of layers. So if you could able to reduce the number of layers, so then you could reduce the build time. So each layer, it will take some setup time, right? So again, that setup time will vary from technology to technology, and kind of say sensors or the actuators you may use, and how precisely. Then you, but like in a thumb rule, like, say, if you want to use a build time criteria, means like let your orientation be selected in such a way that the Z height will be minimum. That may be one of the criterions to fix. That is directly proportional to your build time. Or sometimes you may be looking at quality of the parts that you're going to make. Then your part orientation is also playing a vital role. You may get a different surface finish once you change the orientation, build orientation from one to other. And then you may have another criteria, like the area of the base on which the part is resting. So means wherever you have a strong foundation, then you may have that may be one of the criterions, like, which we need to. Why I'm saying this is, like, the software may suggest some, like, just you, if you import your STL file into your software, and then automatically by default it will suggest some orientation. But whether that has followed the Z height criteria, that has followed the surface quality criteria, or the maximizing the base or the foundation criteria, or mechanical properties criteria, means you cannot expect the same mechanical property. One sample you made with some 0 degree orientation, another is 90 or 45. So it never match, as we know that basically it's a layered manufacturing. So you cannot expect an isotropic property. So that's an anisotropic property maybe you may be experiencing with 3D printing technology. So then how do you, maybe mechanical properties may be the one of your criterion, or maybe for using some external support structure, means like you want to minimize the quantity, the consuming quantity of the support material maybe. So then keeping in mind these criterions, like say let me summarize, say I have some design that it is modeled in this way. So then you can have several possible fabrication orientations. So then if you could orient this in this orientation, and you may have a maximum area of the base. And if you orient this part, you may have a minimum area of contact with the support. And if you are looking for a minimum Z height criteria, this would be the optimum orientation for minimizing the number of layers or the Z height, or the facet roughness. If you are looking at minimum facet roughness, or the minimum volume support you are looking at, and then you may go with this kind of a support as the orientation. So then one can understand the importance of this part orientation while fixing your fabrication orientation. And say if you try to evaluate the surface finish, that a typical two samples, say for example, one sample is made with an angle, say some 45-degree angle to the horizontal plane, and with a layer thickness of X layer thickness, and Y is the length of the exposed part. So if you are trying to orient this in approximately 45-degree or so, and you are building layer by layer, so then you have the error here, or the cusp height, typically it is termed as, means this is an error which you can encounter at this layer and at this layer like this, which you try to find out the cumulative error for this sample. And then you have another sample which it is now reduced your theta value, say maybe around 30 degrees or so, with the same layer thickness X, and trying to fabricate it, which you can see you have come out with more error rather than the previous orientation. So you have more error here. So if you try to say find out the cumulative error in this case, so obviously it may have more error than this. So one can understand the importance of this build orientation. If you are looking surface finish should be, then you have to take a call on what kind of orientation we need to fix it. And then if you talk about the mechanical strength, say you can have two samples. One sample is fabricated with 0-degree orientation, another sample is in 90-degree orientation. And if you try to say distinguish the fracture mechanics of the sample which it has made with 0-degree orientation, and which another sample is made with 90-degree orientation, you have a totally different scenario of the fracture mechanics here. So then one can understand the importance of this part orientation for your mechanical strength and things like that. So then we need to take a call on this kind of orientation while fixing your orientation. So it will play a crucial role. And of course, you can even say talk about the cost, the general cost, the product cost that you are going to say. So typically the total cost of the product that is manufactured through 3D printing. So then you can broadly divide them into four groups. That is a pre-processing cost. So that is, of course, whatever we are discussing, design for 3D printing. So, or the preparation of the code. So all that thing will come here. Like, so you may hire some design people, you may hire some application engineer, or you may buy some software or some workstations, or you may take lease for some softwares or things like that. Then we need to say calculate that cost, the pre-processing cost, and and the build cost, so that is of course the machine utilization cost. So you have the capital investment, and then like we need to say calculate and come out with taking the depreciation things, overheads, and then you can come out with some machine utilization cost of a particular machine or particular model of a machine. So then you need to calculate that as a build cost, and of course material cost. And again, if it is if it requires support material also, then we need to add a model material, cost of the model material plus cost of support material. So that is the material cost. And of course, after fabrication, it will undergo a post-processing methods. So these four post-processing cost, like say it may undergo some furnace treatment, or it may undergo some kind of finishing operation. So then we need to include that cost also, the post-processing cost. So the post-processing cost, it is directly even influencing on this say while designing or while preparing your code. So then, for example, your support generation, if you could able to minimize the support structure thing here, and then your post-processing cost towards removing the supports or the efforts that you put it, then definitely it is getting reduced. So what I'm trying to say, your pre-processing cost, or the design for 3D printing is playing a crucial role here in order to say justify your production cost. So yeah, so then this is typical the cost model for a typical 3D printing process. And again, it will vary from process to process. The setup time will vary from powder bed system to say material jetting system, or maybe extrusion system. So it's not, you cannot generalize, then it will be varying it. So then we'll talk about the next aspect is the support generation, support structure generation. So support structure generation, it is not mandatory for all the 3D printing processes. Like some powder bed system with polymer printing, it may not require any supports. For sheet lamination process, it doesn't require any supports. But majority of the systems, majority of the 3D printing process, it requires supports. So then we need to come out with some kind of thumb rules or some kind of thing which we, how do you reduce this support structure. So then we need to exercise on that, like but software may suggest some kind of default support generation. So then you may have several tools to do this job. Maybe you may use Simplify 3D, or you may use Cura software for FDM based systems, and you may use even some other tools to do this job. But let us understand more about these support structures. So the support structure can typically we can categorize into three kinds of supports. Say the first kind of support, so you have a platform and then you're trying to say build the part layer by layer. So initial layers which you may deposit on direct onto the platform. So typically you may call that as a separator kind of a support. So without damaging your part while say unloading your part, so then you may use some separator kind of a supports here. And then on top of that, so you have a main supports here. The main supports are the one which it doesn't have a direct contact with the model. So, but you have the third kind of a support, CR or a needle kind of a support. So that is very crucial. Why? Because it should, sometimes it may damage your part while removing this supports. Then we need to carefully design these kind of, you have to give special attention, no doubt, for this kind of a supports called a CR or a needle kind of a supports, which are directly contact with the model. So then we need to prioritize, or we need to give a special attentions to particular, and again it depends on the kind of a feature that it requires supports. Some overhang this case, or in some other case it may be island, or it may be a kind of internal feature. So then So then we need to accordingly, we need to vary the support styles. So then this is all designed for 3D printing rules, or the design rules. For one can understand these aspects, then only you could able to generate a sound build setup, or the codes for the 3D printing machine. So, but don't have a perception that support structures is always bad. So, but support structures may be a bless for sometimes, but it need not be the curse always. Say, for example, I have some model. Say, I have the separator or the platform, and I made some separator kind of a supports, and I quickly made this part from in the form of layers, and then I may come out with some peeling effect or some kind of a curling kind of thing here. So in order to prevent that, you should have given some supports here like this, and then even you can eliminate this kind of peeling effect or curling effect. So in this case, supports may be helpful. Say, we cannot say ruled out every time saying that supports are always bad. And again, it depends on the type of material, say, and the technology. But anyway, if you take a typical metal printing powder bed system, so in that case, sometimes it may act as a conductor also, your support structure. But say, well, then one can understand the behavior or the physics of a particular technology which you are going to use, and then that also say influence a lot about the support structure kind of thing. And of course, we need to do a slicing, the model slicing. Then how do you get slice these models? And in continuation with the previous discussion, that is in the last class discussion. So then we'll see that how do you get sliced and how do you generate the tool paths for 3D printing. So of course, once you fix the orientation and once you generate the supports, and then we need to slice the model into layers. And then for that matter, like say, how do you get calculated your say number of layers that a typical model should fabricate in how many layers? Means it's simple. You have a Z height, maximum Z height, and the minimum Z height by layer thickness. So you can find out how many layers that a typical model is getting consumed or getting fabricated. So and then these number of layers, and then how do you get your slice points? So last class we have discussed, like you have the slicing plane and the STL file that is an triangle edge, and that intersection point at that particular Z layer, or that is a ZI. So that is at a particular instant of your layer thickness. Say you need to so get the intersection point with the simple geometry mathematical treatment. So it is a simple intersection of your a plane with an edge. So that's what STL files are more convenient to perform a slicing operation or getting your slice points, the intersection points. So the mathematics involved will be easy here. Relatively, the math involved computationally also it is less expensive than. So once you get this, what you call the points, then we need to join that and we'll get a contour, right? And then actually, we need to focus another aspect here is we need to identify some peak features. What do you mean by a peak feature? Say I may have my model is like this, and I'm trying to slicing it. So then I might have used some 100 micron is my layer thickness. And I may have some features in my model, which is of this curve, which is of say less than my layer thickness. So then definitely this feature definitely will be omitted. Even you can come here, and these are some of the features. It may get omitted because of your layer thickness is more than your feature size. So then we need to identify some of the peak features in our model, and then we need to do accordingly. Say means we need to vary the layer thickness somewhere wherever you identified some peak features, and there the peak features, then you reduce the layer thickness, and like that you can come out with some solution for these kind of peak features without omitting that. You can, so one can understand these kind of constraints of a machine. Say again, it depends on, we cannot generalize this, right? Say what kind of machine you are using it, and what is the layer thickness that the capable of setting, what is the range of the machine that it will take, layer thickness and other things which we need to study, and then accordingly we need to work on that. So yeah, this is in continuation with the previous discussion. Like you have the intersection, your slicing plane and your STL file, the triangle facet intersection. So by using the previous slide, that simple mathematical equation, so you could be able to get this intersection point. Say, for example, if I start from say 1, 2, 3, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 and 9. So then it will ensure that you have a closed contour. So you may have two possible ways, right? Either it can be a clockwise and or the anti-clockwise. So it depends on that particular feature is an interior or exterior. You have some convention should be followed, and based on that you could able to get this contour after joining those the intersection points, so you could able to get the contours. And you, how do you identify which is interior and which is exterior contours? And of course this job will be done by your slicing algorithm or the tools or the softwares which you can will be using it. But how it will be identified, so then you may have some algorithms to do this. So then we need to say based on that algorithm, this is a ray tracing algorithm. So based on that algorithm, then it may identify, and basically it is a kind of hierarchy, right? So you have a root and you have branches, sub branches, or basically you have some parent, child, and such kind of structure that it's getting saved in your data based on the data structure, how it is got. Uh, so, and then once you generate that stuff, the code, that code, say this also we have discussed in the yesterday's class, like one of the contour data file formats are CLI or SLI. Or, this is a common layer interface format called CLI. So this code, whatever you generated, by adopting all the process parameters, and then you got this code. This code will be sent to the machine. So typically, if you see this code, the CLI file format, it consists of say how many number of layers that in your model that consists of, and then the contour data, the first layer, and the layer number, say the coordinate of that particular layer, and then the number of contours, and that the first layer, for example, how many number of contours are there. And it starts with the first contour. The first contour, you have a contour number, it's a closed or open, and then whether it is interior or exterior. In the previous ray tracing algorithm, so then you have the exterior, interior kind of data, and then that contour, and whether it's a father contour or a child contour, so that hierarchy. So, and then you have, let's say, number of contour points, and of course the coordinates of that contour, right? So then it will be saved. So this is for the first contour, and similarly you have second contour, third contour. So how many contours are there at that particular layer? So it consists of all that. That is about the first layer, and similarly you have the second layer, third layer, fourth layer, and the last layer. Up to that, it will be there. So it will be the typical code that you send it to the machine. So once it has sent to the machine, so basically this is the outer skin, right? So then it should be filled with some toolpath strategy, like say, then you may have several toolpath strategies. Say, I have a boundary, then if I'm using a laser based system, so my laser I can move my laser in several possible ways, maybe some horizontal vertical combination, or it may be some raster fashion or some zigzag fashion, or combination of contour and the raster. Or so then, but it dictates your outcome, right? Say, your density. Say if you're using say more overlapping kind of thing, and you may get more dense, but it may take longer build times. So then, in that way, like which toolpath strategy will suit your requirement or your application, or like say you need to use an appropriate toolpath filling strategy for your application, right? Or then there is no such standards available saying that say this will give you this, but and again it will be varying from geometry to geometry, and each object each time it may be challenge for you, like uh, then like one can understand these aspects maybe by conducting some preliminary experiments on that, or some simulation or some modeling, mathematical modeling, or kind of somebody's asking, say, sir, can you suggest some research problems? So then you can think, and then you can say, think in the direction, and then you can pick up some um, problem in this direction, and you can start solving it, right? Say either you can develop some mathematical this one, or use simulation packages for doing this job, or right, conduct some experiments. And our aim is to get the optimum parameter set that it can be. So, and it will vary from material to material, right? So you cannot generalize that how a steel will behave with your laser interaction. It's not same with aluminum, or it's not same with the titanium, right? So the absorption rate is different if you vary the uh, material, right? So then you have several challenges to be addressed. So then one can take up, you have a huge scope to work on these kind of problems. And then last class also we are discussing some STL file problems and all, right? So the mesh repair and the slicer tools, you may use some STL editing tools, maybe some, you may use mesh mixer or mesh lab or magics. You have plenty of tools to do this mesh repair thing, like maybe for visualization, measuring, labeling, painting, haloing, or cutting, or Boolean operations, or smoothing of your STL files. So why it is important is like, unfortunately, once you save your file as STL file, so it will become as absolutely a static uh, image. So you cannot, it won't allow you to do a kind of modification, neither you cannot measure, or you cannot do all this stuff on STL. I'm talking about not on the native format, but you will be sending a STL file only to the service bureau, or the person who have the facility this, and then you will be sending the design. So sometimes, but as we discussed in the last class, like these problems, or these challenges will be addressed by the AMF file format comfortably. But still, STL is going as a de facto standard. But these kind of third-party tools maybe still it's under survival, or maybe huge demand. Um, okay. And sometimes we need to do some visualization purpose, or some flipping of the triangles we discussed yesterday. So we need to flip the triangles, or we need to flip the normals sometimes. And you may have some tools to automatically do some stitching, means some missing facets, missing triangles, or overlapping triangles, or intersection triangles that we had discussed yesterday. So then that can be done automatic stitching, or automatic triangulation, or automatic repair of these problems. It will automatically, or it can be manually. You can go and do manual corrections, or the manual repairs also. It will be supported. And support generation, the basic idea here is um, if you are looking for the support, which you can see, it requires a large base area for this kind of a support. You have a large base area, so then you may go with a block kind of a support. The idea here is, don't use the same kind of a support for all the features. Say I have this kind of a block support can be used whenever I have a large surface base area that should be supported. And sometimes I need to give the support at very narrow or a very thin features. So then you may use a line kind of a support. Or sometimes you have a very small feature, but that requires some support. Then you may use some kind of a point kind of a support. And you have some overhanging projection kind of a thing. And then you may use some gusset kind of a support. And you may have some circular feature that requires some support. So then you may use some web kind of a support. Like this may be available from your software database also. Then it can be even further, it can be explored. Like it is always quest for focusing on the support structure. If it is a metal printing, still it is a tedious. Why? Because your model is a metal, and the support is also in metal. And that if it is a powder bed system, the same material. This is steel, and this is also steel, right? So definitely it may damage while removing your support. Your surface may get damaged. So then in that case, so how do you tackle this kind of a supports? That is a huge task for any 3D printing user. And you may have slicer software, as we discussed, like it can be an STL or OBJ or X3D, 3MF, AMF, or any format. It will slice and it will generate G code from the software like Cura, or a repeater, or Slice 3, or a Simplify 3, or you have plenty of open source softwares to do this job. And these are some of the tools for STL file repair and slicer software. So Mesh Mixer is an open source software for doing STL repairs, and of course NetFab. Magix is a proprietary software. Of course, we need to buy from the Materialize Belgium, but these are open source softwares. Cura Simplify 3D is also open source software for exclusively for FDM based DIY kind of printers. And you may have other open source softwares also for slicer softwares. And topology optimization we discussed last class also. But my focus here is, so now we are talking about design for 3D printing. Say, then how do you generate your lattices? Like what could be the struct size, and what could be the pore size, and things like that. Why? Because you design, but ultimately your 3D printer has to fabricate that. Then we need to consider the constraints of that particular machine, that particular technology, and what kind of a material you're using it. Then we need to see all that, and based on that we need to generate your code, so that will be sent to the machine. So that's the thing where we need to, and if you see in that perspective, then how do you generate a code by taking these kind of a designs which are coming from the tools, topology optimized tools, or generative design tools, or parametric bionic design tools. this we have discussed last class also. Like these are some of the softwares that, and then you may have the idea of uh, introducing a simulation software is also a good idea. Why? Because if you're not done a sufficient homework before you send these codes to the machine, so definitely you have to pay a lot. Why? Because you don't have a luxury. If you are working with the metal printers, so the cost of the material may be going, say, 5,000 to 20,000 per kg. So then you don't have a luxury to waste this powder or the material, raw material. Then so definitely we need to do some kind of a simulation before you fabricate in a real time. So in order to do that, you may have some simulation stuff here. So that's through that simulation stuff you can even predict some kind of distortions in your layers or residual stresses that it will build up. So then that is also can be considered, and then further it will be getting compensated in your designs. So all these will come talk about the design for 3D printing scope. And you have a model optimal support structures is also another task which we need to optimize the support structures, and ultimately it's going to lead minimizing the risks of printer damage or recoater damage once you have a sufficient simulation before you start your real-time production, and minimize the number of build tryouts, and which will predict the impact of post-processing also, right? So then it may undergo some heat treatment or shipping or support removal. All that can be predicted during the simulation studies. And these are some of the simulation tools available. ANSYS additive print. Nowadays, even CAE packages also they are coming out with some add-on modules exclusively dedicated for additive manufacturing or 3D printing simulations from ANSYS or 3D Systems, 3D Expert, and have DigiMat, and you have NetFab from Autodesk. To some extent, it will work. And Hexagon Simufact Additive and Siemens NX Sim Center. These some of the simulation tools or the softwares available for 3D printing. And then how do you get selected your 3D printing technology by material? Why? Because why I'm saying by material, but you cannot process all the materials on a single 3D printing machine, right? That is a constraint in the 3D printing process. So anyway, I don't have much time to elaborate this, but like the idea here is like the material may be polymer, metal, ceramic, composite, or even it can be a functional or electronic shape memory alloys, or it can be a biological food, or nowadays you have innovative materials, innovative applications. So then need not be a standard category of synthetic materials. Even it can be a natural material, biological material also, right? So that is the beauty of this technology. So even it may be a powder form, filament form, sheet form, or a liquid form. And it will vary from all these 7 ASTM ISO combined standard 5290015. As for that, we need to fit them into 7 groups of. So then we need to select, like if you are looking for a polymer, and again, whether it is a thermoplastic or a thermoset, typically it will be resins, photosensitive polymer resins, then we need to go and select a particular technology. And you are looking for metals, and you may have powder bed system or a binder jetting system, or even a DED system can also be work out. But like what kind of material you're looking at, and based on that we need to choose your technology, and maybe sand, maybe other materials. So then polymers, maybe thermoplastics. Under thermoplastic, again semi-crystalline or amorphous, you have plenty of options with you, maybe PLA, ABS in case of amorphous, and you may have a nylon, a 6, 11, 12, PC, PPE, PEEK or PEI for high performance lightweighting materials. These are, and typically you may have metals like stainless steel. You may have a different grades of stainless steel, tool steel. You may have different grades, aluminum. You may have 10 mg, 5 mg, 6 mg. You have plenty of aluminum alloys, titanium, 65, 64, ELI, commercially pure titanium. You have plenty of titanium alloys, cobalt, chrome, tungsten, nickel alloys, inconels, 625, 718, hastrolite, copper, precious materials like copper, gold, silver. You have plenty of material choices under the metals. And ceramics also, you may have zirconia, silicon nitrate, alumina, and you may have silica, hydroxyapatite, like calcium phosphate, cordylate, and you have other ceramics that can be 3D printed. And composites also now, so, in the recent times, there is a huge growth in the composite printing. So maybe FRP, non-X nylon, or a continuous fibers also, carbon fiber, Kevlar fiberglass, HST, or it can be metal matrix or ceramic matrix composites also. So, and even multiple materials, maybe grading, functionally graded materials, metal matrix composites. You have plenty of options to work on this. And other than these standard materials, as we discussed, like wax, sand, glass, concrete for construction applications, living cells, biological skin or food, and so on and so forth. So how do you get selected by application means like we need to further, you're looking for some functional application means like some, say we need to broadly classify, you're looking for form fit, and then what kind of tolerance you are looking at, whether it's low, maybe plus or minus 0.5 or 0.3, 0.1, and then you have to pick an appropriate technology. And if you're looking for high strength, maybe more than 85 MPa or 30 to 85, 30 MPa, then you have to pick from the lot what kind of technology is suitable for your required application, required functionality of that. Special property, if you're looking at some chemical resistance or heat flame resistance or biocompatible, then you have to pick from this. And then flexibly, you're looking at a high elongation, soft rubber kind of a material or the application you're looking at, and then pick appropriate technology. Or from visual appearance, for smooth surface you're anticipating, or transparent kind of a thing you're anticipating, and then pick from that. And textures you have in wood fill or metal fill in case of FDM. So you have full color you're looking at, whether it is in polymer, and in the sand you're looking at, you have binder it in material, so on and so forth. Like among all that 7 processes, then we need to pick from then this important, how do you get selected your technology based on your application and the requirements. And let me come to the last part of my presentation, what the design rules for this 3D printing. So of course, in order to know this design rules, we have to know thorough knowledge about all these 7 processes. Why? Because each process will behave differently. Why? Because it will vary from the raw material, and it will vary from the energy source. It will vary from the physics or the bonding mechanism that is undergoing. So some technology may use binder, some technology may use laser energy, some technology may use heat energy, some technology may use ultrasonic welding. So we need to know about the capabilities or the constraints of each and every process, and then you check your features in your design. Like say you come across some support wall kind of feature, then if you are looking for an FDM based extrusion based system, then you should not even go less than 0.8 mm. You cannot produce this kind of feature in case of with FDM technology, but even it is possible. You can go up to 0.5 mm if it is a laser based or it's a stereo lithography or a VAT based system. So why? Because your energy source is different here. It is an nozzle, a physical nozzle. Here you may have the laser or the UV light. So typically you may come out with the different values of these features. And then you may have some unsupported wall. Then we need to follow some minimum requirements. If at all, then sometimes we need to change the design. That's what I'm trying to say. We need to understand the constraints of each and every process, and in check. You scan your design, all the features that are there in your design, whether it's capable of printing, whether it can take up that feature, and then say supports overhang is 45, or it may be always is needed here. Like it depends. And you have some embossing and engraving option, the features on a single product. Then how do you ensure that? What could be the minimum dimensions that you could get it through embossing option or engraving kind of features? There are some horizontal bridges. Then it's not, you need to go with 10 but here it is not needed. Why? Because it basically FDM will work on as for the demand, it's getting extruded, right? But here, if you take SLA system, you have a vat of liquid. If you take here, it is a bed of powder. So then that's what, like how your part is submerged, means whether it is surrounding is a powder or surrounding is a liquid or surrounding is open. So it will dictate several things, right? So, and then you may be having a minimum size of a hole that you can produce through FDM, maybe 2 or 0.5 in case of SLA, like that, and it may be 1.5 for SLS system. And then the same features, if you try to explain with the other set of 3D printing processes like material jetting, binder jetting, and directed metal DMLS, or a typical powder bed system with metals. So you may have different values of these features, right? So these are some of the design rules. And further, even you have some connecting, mating parts, moving parts, and then what could be the tolerance levels that we need to maintain whenever you have mating part or moving part. So it will vary again from the process to process. The values will be varied, and you have some escape holes, and then what could be the minimum size of escape hole for this kind of features. It doesn't require. Why? Because as for the demand, it is depositing, but again we need to take care about these kind of escape holes if you're working with VAT system or a powder bed system. And the minimum feature size of this one, or maybe pin diameter, or you have some tolerances. So then this is about these three processes, and it may be varying from the one process to other process. Like, and then finally, the if you visit Purdue University, there is a C lab, and they have set up some design rules for additive manufacturing. So what they have done is they have come out with some matrices or some kind of weightage. Say you have some product that is getting 3D printed, and then quickly you can scan your product against all these matrices. They have divided into complexity is one matrix, and then functionality is another one, material removal, unsupported features, thin features, stress concentration, tolerance, geometric exactness. Just you can scan through your and get the score of your design against all these parameters. And then if your score is too low, then you do not much worry about it. And if your score is too high, sometimes we need to redesign your product. Why? Because your machine cannot produce. So then once you evaluate this and get the score, and based on that, you can take some decision. And of course, you may follow some ASTM rules, but ASTM, you don't have much standards as on date. But so let me conclude my talk. So giving some fabrication challenges in 3D printing process, like say, um, in a conclusion, right from the beginning of my talk, also the major challenge could be the complexity of EM production process. What do you mean by that? Is say um, each time is a challenge. Why? Because your parameter set is we need to say consider several stuff into thing, and we need to um, check some implications for this aspect. Say you need to even say, if we talk about the design aspects, like what is the geometry, and then overhangs and support structure, just now we are talking about also, and then material type, and again it will vary from the raw material source. If it is a powder bed system, then we need to check the powder size, particle size, and the powder purity, and so on and so forth. And if it is a filament, whether it's as for the standards, the raw material, the filament, or things like that, and which we need to look at. And then otherwise, like the layout, like which you are talking about, whether it's a horizontal or vertical orientation, or object proximity, or you have some chamber filling. How do you make use of your build chamber? And then process related parameters, like if it is a laser system, laser intensity, speed, and exposure patterns, and roughly you may have around 180 parameters that may change your um, things, right? And then this is one side. And then during post processing, like you may use some heat treatment process, short pinning, polishing, right? And then we need to consider the several stuff, like the surface tension, curling effect, staircasing effect, previously also we have discussed, and volume contractions, heat dissipations, anisotropy in z-axis, and some micro melting, or there's a change of material properties. So the implications is, like say, as of now there is no a set of design layouts or whatever we have discussed here. There is, as on date, there is no um, uh, standard or nothing literature is support that you can follow. No, as on date, nothing is there that way. So every time it is a challenge, and every object we need to come out with your own parameter set. That should be. And the practitioners needs to tailor the production process to each specific object. That's what I'm trying to say. And the adoption, so you use of new materials. So you have each and every day the new material will be added. So then it's we need to even spend a lot of time, years together, to develop a kind of a parameter set, optimum parameter set. And it may have more experience needed for at least next 5 to 10 years before your new object can be made with less efforts. You talk about design for 3D printing. So yeah, it's then definitely, as I already said, some simulation models will also shorten your development times, maybe in future, or even it can, there is a huge potential to work on the simulation kind of a models that it can even predict. Let me summarize, like the fabrication challenges, maybe as I said, like standardization of the process is not happening so far. Then you don't say there is a huge inconsistency from machine to machine and run to run. Maybe reasons several in the previous slide we have discussed. Maybe we need to say it need badly some kind of standardization of the process is needed. And post processing requirement, as we know, that it will consume a lot of cost, time, the kind of stuff, manpower, and things like that. And certification of the parts is also another. If you have some standards, certification, and qualification, and then you can judge in a position that you have made bad part or a good part, right? So then certification is lagging is another challenge. And there is a huge potential health hazard is to particular process, but not all the process, but definitely that is another challenge. And integrity of the digital data, that is another aspect, like the blockchain systems, which we need to cyber security kind of stuff for your designs. And last but not the least, of course, the kind of IP protection, is another challenge. So let me summarize what I have done for the last 1.5 hours. So we have started with an importance of the 3D printing design, and we have thoroughly discussed the process plan. Under that, the importance of the part orientation, support structure generation, model slicing and tool path generation, and topology optimization bionic designs, and the selection of the 3D printing technology by material, by application, and design rules for additive manufacturing. And finally, we have discussed the fabrication challenges in 3D printing. So yeah, these are some of the facilities which we have at NIT Warangal. Even you can go through it. Yeah, and then I will be stopping my presentation here and concluding it here at this point of time. And then if you're having some queries, then you are most welcome. And then I'm very happy to answer those queries. Yeah, it is over to you.
Okay, participants, if you have any queries, you can unmute yourself and ask. Else you can put it in the chat box. Any queries from your end?
Okay, sir, we are not getting any queries from the participant side. We
Okay.
can conclude here, sir.
Yes, yes. Okay.
Sir, again, on behalf of Department of Production Engineering, VSSUT Burla, my own behalf, as well as on behalf of the participants of this Hotel FDP, I thank you for giving your consent and delivering 2 nice sessions yesterday and today as well. Sessions were really valuable as well as informative. And we look forward for future collaborations with you as well. Thank you, sir. Thank you very much.
Yeah, thank you, Dr. Mahapatra. Thank you. Thank you, one and all. Thank you.